So when we used our continuity equation before, it was a box. It had a top and a bottom, and it had sides, and it had front and back. That only makes sense when you have a confined aquifer, right? Because the confined aquifer is defined by a confining unit on the bottom and a confining unit on the top. What if it's unconfined? Well, we have the confining unit on the bottom, but then we have the water table on the top. What defines the water table? Well, that is the hydraulic head. So now we have the situation where the top of our control volume is not constant. The top of our control volume is set by the water table, which varies according to the head. And of course, we wrote our whole equation to be able to track the head as it changes through space. This is a problem. We have to use an entirely different equation to account for this behavior. So we have a situation that's something like this, where we have potential lines, of course, that are perpendicular more or less to the water table, which is here. This is the top of our box. And so we still have flow coming out, and we still have flow coming in. However, now the top of this thing is the water table, and the bottom is still a confining unit. So we need to be able to handle this sloping water table, which suggests that we have these sloping potential lines, which means that our flow lines are going to do something like this. They're going to converge, and that's going to be complicated. So we're going to cheat. We're going to cheat the way Dupuit-Forchheimer cheated. We're going to use a set of assumptions that are called the Dupuit-Forchheimer assumptions. There's actually a whole list of them, but we don't really need to know all of them in particular. The key points here are that when you apply the Dupuit-Forchheimer assumptions, you assume that the hydraulic head in the vertical is 0. So the head's not changing in the vertical. Clearly it should be because of the water table, but we're assuming it's not. How do we get away with that? Well, if the water table is just sloping gently, this curve is not so much, and then there isn't that much of a vertical gradient. So if we're away from a seepage face or away from wells or anything that's putting in or taking out water, it's not a bad assumption. We also assume that the bottom confining unit is our datum, so that we measure head above that. And that allows us to measure the thickness of the aquifer, to relate the thickness of the aquifer, bounded on the bottom by a confining unit, water table on the top, to the head. Okay? So if we do that, one of the things that happens is our entire z direction drops out, so we no longer have z in our continuity equation. However, when we did our delta x, delta y, delta z, we no longer have delta z, it doesn't drop out, it ends up being expressed as head, right? Because the z component of our control volume is head. And so it doesn't disappear. It doesn't end up as a volume on the other side like we did before, and it sticks around in here. So now we have a bit of an issue in that we've got heads here that are basically squared, and they're single over here. And I can show that to you by using the chain rule. Use the chain rule, as you recall. And that is, remember, if we take the derivative of h squared, right, that's equal to 2 times h dh. Let me change by 2 so it doesn't look like the partial, so we don't get confused here. So that's 2 times h times dh. Okay, so we call that the chain rule. And so if we divide both by 1/2, right? We put 1/2 over here and then cross this out. And so if we take this term, which appears here, right, we can do this substitution, and what we end up with is h squared, right? So we have, and also because we're combining h here, and we're assuming that we're using the chain rule to basically move that h in there, we end up with a second order derivative of h squared. And so we have partial h squared, second order derivative of h squared, plus second order partial h squared times over the partial y squared. And then we have the same thing on the right-hand side, except that now we have this, we had this 1/2 over here, and so that is going to make a factor of 2 over here on the right-hand side. And again, let me change my 2 so that it doesn't look like a partial. There. Okay. So this is our equation for unconfined flow. And basically, we're only looking at the horizontal direction. We go in the x direction, the y direction. We're not predicting anything in the z direction because we basically made that go away through this assumption that we applied right here. And again, we can make, if we say the whole thing is steady, then the right-hand side would be a 0, and then we would say for steady flow, once again, we have our second order partial is equal to 0, and notice that we have h squared instead of h before. So I didn't say much about storage on the right-hand side here. So notice that I've got specific yield instead of specific storage. So if we recall, the difference is we use specific yield for unconfined flow because that's drainage out of the pores. That's when the pores are actually emptying out, as opposed to specific storage, which is elastic release. When we reduce the pressure, the grains expand just a tiny bit, and that produces a little bit of water for storage. So this is going to be a much larger term in unconfined flow than it is going to be in confined flow, making this assumption maybe a little more difficult to make, assuming steady flow, because that storage could actually be quite significant.